Recording.
Again, welcome to the lab session for today. It's for Physics 4C. And it's today is March 29th. Next week, we have another lab on heat engines. Basically, we have a bunch of engines that need to be worked on. For that lab, for next lab, we're going to need to work in teams. So we're going to probably, we'll see how it goes, okay? Because you will have a bunch of engines and you're going to be calculating a lot of their properties. And those engines are actually cycles, I should say. They're actually three stroke cycles, three processes, each and every one of them. So you're going to be calculating everything that has to do with this, with the engines. One of the things you'll be calculating next week, and I think we need to introduce on Monday when first we come from chapter 20, and that is the entropy, which is another state variable in addition to the temperature, in addition to the volume, in addition to the pressure, in addition to the internal energy. Turns out that there is another state variable that we need actually in this case, and that also during a full cycle will be zero. So if you go from your starting point and go a whole cycle, it doesn't matter whether you're going through a heat pump or you're going through an engine, you're going back to the same point on the PV diagram. In this case, the entropy, the change in the entropy should be zero. Provided, of course, that we're talking about a closed system. It turns out that the second law, actually, of thermodynamics will make it in such a way that there is, at least in, for the entire universe, the entropy is always increasing, okay? Yeah, okay, good. So, so that is something that we need to do for next lab, but for today's lab, it's all about the adiabatic process. So let's go through the instructions of the lab. I know a lot of you are not coming live anymore. I'm hoping that you're still doing the discussions, you're still going the stuff that is doing this ones, and you guys need to take care of that as soon as possible, and so that you catch up, because we have a midterm coming very soon. So it's really going to matter exactly to catch up with everything in here with your grades and everything. Anyway, so this is the lab. Let me share with you the screen in here for this lab. So the adiabatic process is just hot from the oven. We just basically discussed the entire topic today. And it's a process where there is no heat exchange, okay? In this lab, we're going to follow a method by Richard. That's how his name is, not Richard. I think it's probably an American now, it's Richard in English. Anyway, the method basically involves an adiabatic process, an adiabatic oscillation basically of a mass suspended on a gas. That is where the restoring force in this case is going to be the pressure being exerted by the gas on the mass that is suspended on the gas. So this is basically how the idea is. And then if you find the oscillations, the frequency omega, in this case, you can find the value gamma. And gamma is the ideal, is the ratio of the specific heats, basically the gamma ratio, which is a number which has no units. It's the molar specific heat as constant pressure divided by the molar specific heat at the constant volume. So that is basically the purpose of that. From there, if you don't know what the gas is, you can tell, at least as an indication, what type of gas it is. Is it monoatomic gas if gamma is 1.4? Is 1.67? Is it a diatomic gas if gamma is 1.4? Is it a polyatomic gas if gamma is 1.3? So, as usual, leave the objective toward the end. Basically, I already stated what more or less we'll be doing, but that's not exactly per the activities. Okay, sometimes the adiabatic process in some of the literature is referred to as the isentropic process. The reason why I didn't use this term in here is because I did not introduce the concept of entropy. Isentropic means that the entropy doesn't change. And because you will see that the definition of the entropy is actually the ratio of the heat during an infinitesimal process over temperature. So if there is no heat exchange, then there is no change in the entropy. So that's why the idea sometimes is referred to as an isentropic process. because we would want to describe everything in terms of state variables. So the processes that we talked about are, and again, we're not going to talk about this one, okay? But this is another process. So the 4 processes that we have discovered: isothermal, temperature is a state variable. So we'd love to talk in terms of how this temperature doesn't change, okay? That is process. Isobatic process, the pressure is also a state variable. So we would want to talk about processes where the pressure doesn't change. So that's an isobaric process. An isochoric process, and sometimes referred to as isovolumetric process, where the volume, which is another state variable, doesn't change. Similarly, because heat is not really a state variable, but it's a quantity that depends from the transition. In this case, the state variable entropy doesn't change. So if you don't know what the entropy is, and we did not discuss this in lecture at all, so I don't blame you. So you use still the adiabatic process. So this is the process that we're talking about in here, the process where there is no change of heat. So next week, we'll introduce the concept of entropy, and we will use this exchangeably, basically. We refer to each and every one of them the same thing. This is just a word of caution, because you might be taking a class in chemistry down the road, or really took class in chemistry or any other process. I mean, if you're going to be in a chemical engineer or mechanical engineer or some field that uses thermodynamics, you will see probably this word instead used. And sometimes they use them in the same context, in the same text, probably 2 or 3 times interchangeably. So that is the meaning of this, okay? The enthalpy has to do more with other quantities that is actually also for different kind of reactions that at this point we're not going to be dealing with. The 4 processes that we need to focus on for physics 4C are these ones: constant temperature, constant pressure, constant volume, and no exchange of heat or constant entropy, okay? Because you cannot really say constant heat, because it doesn't make sense. There is no such a thing, okay? So we discovered the ideal gas law, PV equal to nRT, and Mr. Boltzmann came up with an interpretation for it. It has to do with the kinetic energy. And during an adiabatic compression, does the temperature increase, decrease, or stay the same? So there is no heat exchange. And this is confusing, because I know almost every year when I give exams, I ask, and this is not going to be different for you guys, by the way. Okay? So be on the lookout for that, okay, to calculate the entropy. And there will be processes that involve, for example, isothermal processes. An isothermal process, because the temperature doesn't change, does not mean that in this case, the entropy is not changing, okay? The entropy, the change in the entropy is 0. So when you calculate the entropy, do not tell me, hey, because it's an isothermal process, the temperature doesn't change, and you plug in the wrong formula, for example, ln of T final of ln over T initial, and that is, since the temperature is the same, you tell me it's ln of 1, which is 0, therefore there is no change in entropy. That is the wrong formula to apply, because that works when the temperature changes linearly, I mean, at least, I'm sorry, in the dt fashion, and then we're going to come into the calculations of the entropy. So the point being in here is, this is an adiabatic process, and it's similar to the calculations with that. So the fact that the temperature doesn't change in an isothermal process does not necessarily mean there is no heat exchange. In here, the fact that there is an adiabatic process does not mean that the temperature is constant. So there is no exchange of heat, true. But in this case, the pressure is changing, the volume is changing, and the temperature is changing. Everything is changing. So that is the point in it. The energy is changing in this case, but we have a compression. We're going from an initial volume to a final volume that is smaller, because the volume is going down. And remember, PV to the power gamma is constant. So because it's a compression, the pressure must go up, okay? Since the pressure is going up, and if you use the other expression that I talked about in classroom, TV to the power gamma minus 1, and that is also equal to a constant. Since V is getting smaller, so the temperature must going up. Okay, so this is in a nutshell to this question. There was another question before this one. Okay. If a monoatomic gas is compressed to half its initial volume, by what factor does the pressure increase. Again, in this case, you're going to use PV to the power gamma is constant. So if the volume shrinks by a factor of half, okay, that means V final over V initial is basically 1/2 to the power gamma. So the pressure in this case will increase by 2 to the power gamma. And this is a monoatomic gas, so it's the gamma in this case is 1.67. So if I do the calculation in here, let me pull the calculator. So the volume went down by half. That means the pressure will increase by 2 to the power gamma. Okay, so it's going to be 2 to the power, and gamma in this case is 1.67. So it's going to be increased, the pressure will increase by 3 volts, 3.2 volts to make sure, okay? But when you answer this type of questions, I really need to see the reasoning in here. Again, if you guys have difficulty with it, we can discuss it in classroom. Again, the question says, the volume shrinks by a factor of half. But I know, do I have notes in here, comments in this thing in here, commenting to it? I love the old PDF writer, because this one is not really easy to. This is for signature. I just want to write a comment. Can I sign with this thing in here? Okay, so we know, and man, I don't want to do that. This is P, V to the power gamma is constant, it doesn't change. This is what an adiabatic process is. So if this volume goes down by a factor of 2, that means the pressure has to go by a factor of 2 to the power gamma. So that 1 over 2 to the power gamma times 2 to the power gamma stays the same constant. So the pressure must increase by a factor of 2 to the power gamma. But they tell you it's a monoatomic gas. And for a monoatomic gas, gamma is equal to 5 over 3, okay? So this will increase by a factor of 2 to the power 5 over 3, which is 1.67 really. So it's going to increase by 3.2 basically. So that's the answer to the question. Now we're going to do it for a diatomic gas. For a diatomic gas, gamma is not 1.67. It's actually 1.40. So we're going to put 2 to the power 1.40, and we'll find a smaller increase than before. Okay. And for polyatomic gas, use the value of 1.3. So for a polyatomic gas, is going to rise to the power of 1.3. Okay, 2.46. So in here, just by examining the process, if the gas is inside an isolation, thermal insulation, that is, if thermally sealed, and then you take the gas and you compress it down to about a factor of 2, measure the pressure, look at the pressure, see what's going on. If the pressure goes by a factor of 3 point something, then you know you're dealing with a monoatomic gas. Otherwise, depending on which of the other values are dealing with it, the atomic gas. Does this make sense to you guys? Yes or no? Does it make sense? The question? I can't see the comments. Yeah, okay, very good. So the question 2, which we discussed at first, I'm sorry, I skipped the version 1, we came to this one. During an adiabatic compression, does the temperature increase or decrease or stay the same? For this one, we're going to use another, the other relationship, TV to the power, is the pressure? I'm sorry. So we have to use the pressure now. Okay, and this is one of the things that you're supposed to prove in here for the adiabatic pressure, adiabatic process. So the law in here that we need to worry about in here is P to the power 1 minus gamma times T to the power gamma is constant. During a compression, the pressure increases. And this factor in here is less than 1 because gamma is more than 1. Okay, so this goes down. That means this number also will go down too. The temperature will go down too. Wait a minute in here. Yeah, it goes down with the 2. Okay, I probably might have said something else earlier. So during the adiabatic pressure, because this factor is less than 1. Okay, so it's actually on the other side. It's a constant times P to the power gamma minus 1. Then it's clear from there that the temperature and the pressure will go up and down with one another, although not linearly, not in a linear fashion, because of these powers all over the place, gamma and gamma minus 1 and everything else. In other words, since the question is on temperature, it's going to be some constant times the pressure to the power gamma minus 1 over gamma. Okay, and this is actually a positive number. So in this case, as the pressure goes up, the temperature goes up. Yeah, I think that's correct, what I said before then. Yes, that's correct. Yeah, what I said before is correct. Okay, so during an adiabatic compression, does the temperature increase? It does. Okay, stays the same. And if there is a change in temperature, how can this be if there is no absorption or expulsion of heat? Okay, so the temperature goes up, no heat exchange. So what's going on? Okay, so what's going on in this case? Remember, we're going from an adiabatic on low temp to a high temp this way. This is what the compression means. This is what the temperature means. I mean, the pressure means. We're going up from a low temperature to a different temperature. No heat exchange, but delta U in this case, still a positive number because W is positive. So there is work in here to compress the gas. And that work will result in an increase in energy, and the increase in energy is translated to an increase in temperature. So that is basically an answer to that question. Does this make sense to you? Because delta U has to do with delta T. If there is an increase in temperature in this case, there is an increase in internal energy. Where is that energy? Because we're compressing the gas. So we're doing work on the gas. Does this make sense? Good. Okay, very good. So let's share the screen now and continue with the next questions. Okay, this is a relationship I didn't write. This is, I just wrote it, okay? And this is in a TV diagram. This is in a TP or a PT diagram. And we wrote the one with the PV diagram. In the PV diagram, PV to the power gamma is equal to a constant. In the TV diagram, it's TV to the power gamma minus 1 is a constant. In the PT diagram or a TP diagram, it's T is equal to a constant times P to the power gamma minus 1 over gamma, okay? So in here, you're supposed to do the algebra in here and answer this question. I think this question is easy. Then you're supposed to click on this link. And once you click on this link, you're going to be taken the animation. Let me just give you the theory basically on it. So let me look at the picture. Do we have a picture in here? No, we don't have a picture. I'm going to go quickly on it. So this is the theory in a nutshell. Let me go into the animation in here quickly. Where is it here? Let me move this to the other screen and stop sharing this screen and share with you the actual experiment. This is the link basically for the animation. In here, we're taking a volume of 8 liters. The pressure of an atmospheric pressure, basically, okay? And then an amplitude in here of oscillations is basically how far this can go up and down, okay? And right now, it's a triatomic gas. So if we can change it to a monoatomic gas, now it's a monoatomic gas. This is the different gamma. Then this one, which is a diatomic gas, and this one that is triatomic gas. So we're going to go back into that gas. So basically, when we release a particle, it's going to fall. As it falls, it's going to compress on the gas. When the gas is fully compressed, in this case, it's going to repel it back. So now it's going to actually oscillate. And if we measure the frequency of oscillation, we should be able to get the actual, so we're going to take it up and then drop it. And then it's going to oscillate around some equilibrium. And in this case, you get the value of omega. Here is the value of omega. So I'm going to stop this one and do another simulation. So basically, the equilibrium is here at 0. So when we let go of it, it's going to come from an outside of the equilibrium and then start to oscillate. This is what is known as Richard experiment, okay? And in this case, you will find that the omega actually is related to gamma. If you know how to measure omega, you're going to find gamma. So again, we're going to stop this. And we're going to do another measurement. Each time you do a measurement, of course, it's simulating the real situation where you'll have a different reading for omega. And you're going to repeat this one several times. Of course, this is for a monoatomic gas. If I'm going to do a diatomic gas, I'm going to find a different value for the omega because gamma has changed. And this equipment is sensitive enough sometimes to these changes, okay? I'm going to stop it again. I'm going to find a lower value of gamma because now a lower value of omega because gamma went down. I'm going to stop this one in here one more time. I'm going to change the gas to, again, a triatomic because gamma is actually less for a polyatomic gas than for a diatomic gas. So I expect the value of omega to even be less now, okay? So that is basically what I expect to see now. And all of these values are in line with the theory. So if you're interested in the theory behind it, basically the force now exerted on this mass, and you apply M equals to F equals to ma, and A in this case is this acceleration going back up and down. All you have to do is find the force. When the gas is disturbed, in this case, it's pulling back because of the difference in pressure. And the difference in pressure has to do with the change in volume in this case, because the volume went up in this case, so it's pulling back the gas. When it was compressed, it's pushing back on it. So in this case, if you follow the theory correctly, is going to give you the different oscillations in this case. So the force is going to be pressure times the area. And the area is just going to be whatever the area of the shape is, okay? And so if this is pi r squared, this is going to be this cross section. Of course, you have to find the radius and all of that. This is a very difficult experiment to do because of the leak in gas between the sides of the cylinder and the mass. You really have to make it so that it's tight. There is no leak in it, but not too tight so that you have to get not to basically to ignore friction. Otherwise, friction will come into play. So to slow it down. So you do this experiment. That's why when you do it in real life, you have to really do it very quickly and then record the reading of the period. Then in that case, once you find the period, you find 2 pi over gamma, which is 2 pi over t, which is the omega. So you do it and then you stop. Otherwise, it's going to oscillate in a dampened oscillation and stop at the end. Okay, and that's not what you want. You don't want it to stop. At least to give you some significant oscillations, several oscillations before it stops, give you the value of omega. You repeat this experiment and again and again and again. Again, the sites in here play a major role in terms of this thing in here. Okay. Cannot move this thing one way up or down. Anyway, so let's continue with the instructions. Let me stop sharing that screen and share with you the PDF file. What is the PDF here? So if you're not interested in the theory, here is basically where the period is. Obviously, omega and gamma, omega squared is proportional to gamma. That's the main thing in here, okay? when gamma was changing from a polyatomic gas to a diatomic gas to a monoatomic gas, in that case, gamma was increasing, but actually we started with I mean, I think when you click on the link, this link is going to give you in a triatomic gas. So it's going to give you in the increasing values of gamma. And in doing so, the value of omega will also be increasing because there is proportionality between gamma and omega squared. What is different in here is the pressure in the gas, and then the area of the gas, and then the mass of the object times its volume. And that's in a nutshell what everything you need for this expression in here, okay? So that is the constant of proportionality. That is the slope of this object in here. Okay. The volume is not the volume of the mass, it's the volume of the actual gas inside, okay? So, and this T is not the temperature, this is the period. I hope that you know these variables in their context, because T equal to 2 pi over omega, that is the angular velocity, and so this must be a period. So this question in here, verify that the expression given, okay, by the way, I forgot to mention this, but it's an important thing. If you really want to delve into the theory for it, this is where you can find a good link in Wikipedia. So you can pull that experiment from there and look at the details for it, at least not the experiment, the theory behind it. But this is in a nutshell what omega is going to be as a function of gamma. This is an old method on how to find gamma for different gases. So now verify the expression above has a proper period oscillations as period. So basically this must be have the units of 1 over second. Okay, gamma has no units. Pressure is going to be in Newton per meter squared. This is meter squared, meter to the power 4, I'm sorry, because meter squared and meter squared is meter to the power 4. So, and then this is the mass, and the mass in here is in kilogram, and the volume is going to be in meter cubed. So so you'll have meter 1 over meter squared, and kilogram. Yeah, there is another meter in here too, in the Newton. Kilogram meter per second squared times a meter to the power 4. That's a meter to the power 5, divided by meter squared and the pressure, which is the area. So that's going to cancel. You're left with a meter cubed, and there is a meter cubed, so that cancels everything. And there is a kilogram that cancels in this here. So you'll be left with 1 over second squared in the square root. So that's going to be so in other words, do a dimensional analysis. Pressure is a Newton per meter squared. Area is meter squared. So this whole thing is meter to the power 4. And Newton is kilogram meter per second squared. And mass is in kilogram, and volume is cubic meter. So if you sub everything correctly, you're going to get omega to be as units of 1 over s, 1 over second, 1 over time, as it should be. So again, go back to the theory. If you really want to have more details on it, this is the expression for it. And this is what you're verifying in here in this question 5. Question 6, using the above expression for omega or t, find the expression of omega. So you just basically square this expression. Is going to be an omega squared times mv divided by gamma, divided by p times a squared. That should be gamma. So we want to solve this one for gamma. Calculate the angular frequency for a gas pressure of P equal to 1 atmosphere, and you need it in Pascal. You need it in Newton per meter squared, and a volume 8 liter. 8 liter is 0.008 cubic meter. And a ball meter diameter of 1.6 centimeter. So the area is going to be pi times this divided by 2 squared, because this is a diameter. And we're just looking at the cross-section angle in here, okay? We're not looking at the entire outer surface. It's not 4 pi r squared. We're just looking at this cross-section that's going up and down, the area, okay? That is where the force is exerted on that cross-section area. So it's going to be pi r squared. And r in this case is 1.6 divided by 2. It's 0.8 centimeters. So don't forget to multiply it by 10 to the negative 2 to convert into meters. The mass is 10 gram or 0.01 kilogram. When the gas is monoatomic, so you have gamma being 1.67, and you would want to find omega. And you do the same calculation for 1.40, and you do the same calculation for 1.33. Does this make sense to you guys, this question? Both of this and this. Good. Okay, very good. So let me continue sharing the screen. Share. Now we have to do some work in that lab in there, okay? So using the link above for the simulation, that's the GeoGebra link, select the slider for a monoatomic gas. So we're going to do a monoatomic gas, okay? So the green slider takes you back to the monoatomic gas, and do not change the volume, the pressure, nor the amplitude. Leave everything the way it is. Click and go and record the angular frequency in table 2. Basically omega, okay? That's what you need. Repeat the process for the diatomic gas. So we're going to do 1 trial, 2, 3, 4, 5 trials, and find the average. You're going to do the same thing, 5 trials for a diatomic gas. Move the slider. 1, 2, 3, 4, 5. You're going to find another omega average. You're going to do 1, 2, 3, 4, 5, and then find another average. So you have 3 of them. Now do these averages compare. How do they compare to these values? Gamma 1.67, 1.4, and 1.3. Okay. Are the errors acceptable? So this, or take them as known values. So what you do in this case, if I'm calculating the monoatomic gas, I take this average minus this value divided by this value times 100% in absolute value. So if this number happened to be less than 1.67, it's going to be positive. If this number happened to be more than 1.67, it stays positive. So it's always positive divided by 1.67 and times 100, that's going to be your error. You do the same thing for this one, comparing it with this one. And you do the same thing comparing this one with that one, and you're in business. Now you're going to tell me, are the errors acceptable? If it is more than 5%, there is a big problem. And typically in this lab, if you do it in the actual lab room, you're actually going to have a lot of errors, okay? As I mentioned before, it's very hard to do this lab because of the fact that if you make it too small, there is not enough pressure to push it up and down to begin with. There is a gas leak in there, okay? And the whole theory breaks down. And if you make it too tight, then there is friction also involved. So in reality, this lab is very hard to get very high precision, but that's basically the nature of labs anyway. So you always are thinking of getting better, basically experiments to find things that give you better results. And the results, yes, at the end could, for example, give you a different value. If you are doing extremely carefully your lab and you came up with an impeccable lab activity, and the theory breaks down, then in this case, the blame on the theory. But I don't want you guys to blame too much of this theory because this lab is actually, even in the actuality, is not an easy lab to do. Okay? So the effects of volume in this case, so what you do in this case, you're gonna, in this, we explore the effects of change to a diatomic gas. So we're gonna be using 1.4 gamma for gamma and use the average value found above. Change the volume and fill the data in table 3. So basically, use this value for gamma, the one that you found in here, change the slider to that gas, and fill the table for 3. Keep on changing the volume now. So you have different values in liters in here. Don't forget to express the volume in cubic meter. Okay, and find the inverse of it. Let me tell you why that is. Let's go back into the expression. If I square omega squared in here, I will find gamma, which is your average that you found. And this is P A squared over MV. And these values are basically the mass. Let me go back into the link. What is the share link? I'm sorry, stop share. Share this link. So this is what they're saying. Move this one to here and use for gamma the value that you found on average in there, okay? And then change the pressure, we're not going to change it, so you know what the pressure is. Now we're going to change the volume in here. So we're going to start, let's say, for example, with 4 liters. Okay, 4 liters. Can I do that? Oh man, I need to change this value in here. Okay, so this is no good. There is a flaw in here. I need you guys to we'll fix it. Okay, I'll fix it. Okay, please, because I cannot change the value in here for this one in here, because if I do start, stop. Okay, so I need to change this activity in here so that you guys can do this lab. So there is an issue right now. I cannot change the value of the volume, so I'm going to fix it so that you can change the volume. But you're going to change the volume. You have the pressure. You have everything. So technically, you should be able to go do this part. Let me stop sharing. I'm glad I did this now with you guys. This is part of the things you do online. Sometimes you run into situations where the simulations that you make have issues with it. So I'm hoping that you guys, hopefully before tonight, you will have it updated, okay? You will have the same link, so it's not going to change. The only thing that they're going to change is the fact that I'm going to fix that. So once you change the volume, you're going to put 1 over V, because remember, 1 over V is coming in the denominator as the x-axis in here. And this is omega squared. And the values you get from the table are going to be the different frequencies omega squared. So you're going to have a line in here where omega squared is a function of line of 1 over V. And you're going to find the slope in here, okay? Use your favorite method to find the slope, and then that slope should be gamma squared, how well your simulation is compared to the theory. So in this case, I'm going to, you're going to have, because right now you cannot do this, because I don't know, unless it's in my system, but I doubt that this is the case. I will fix the GeoGebra basically activity in such a way that this will allow you to change the volume, and you will have a nice linear function with the slope being exactly gamma times what that stuff is, gamma PA squared over M, okay? And then the conclusion. Barring that issue with the volume, you cannot change it right now, which is a problem, okay? I hope this lab is clear. Yes? Okay, very good. So I'm gonna stop the recording right now. I cannot expect you to continue because I have to finish this lab. I mean, I have to fix that issue. So you can do the first part fine. So if you want to stick around and do it now, that's great. If not, you can leave, but send me a reminder if you don't see it updated at worst by this evening, okay? That this activity has a correct way so that you can change the volume and continue with the second part in trying to verify the relationship between omega squared and the volume in there, okay? I'm gonna stop the recording, and then I'm going to stop my video and my audio, but if you choose to stay, you can just shout out or speak out or tell me that you have a question, and then I will give me about half a minute or so to come near the computer and answer your question. Make sense? Yes? Okay, very good. For those who are choosing to leave, I'm gonna see you guys next Monday because there is no class this Wednesday, okay? Just another reminder, okay, because of the holiday. Okay, so I'm gonna stop sharing, stop recording first.